When we return a sample from Mars, could we identify life in that sample?
Can we go there and sustain ourselves without harming Mars if there's something on Mars that could be harmed?
Hi, I'm Jim Green, Chief Scientist at NASA, and this is Gravity Assist. On this season of Gravity Assist, we're looking for life beyond Earth.
I'm here with Dr. Lisa Pratt, and she's NASA's Planetary Protection Officer. She plays a critical role in overseeing and approving how NASA implements planetary protection requirements for all our planetary missions, both robotic and human spacecraft. Welcome, Lisa, to Gravity Assist.
Hey, thank you, Jim.
You know, you've had a distinguished career in biogeochemistry and astrobiology, and the Planetary Protection Officer name, that sounds really cool. In fact, I received letters from kids all over the world, and one of them called your position the Guardian of the Galaxy. So I can't help but think that every time I talk to you. But let's start with the basics. What is planetary protection?
Jim, I wish I could tell you that I was in fact the guardian of the galaxy, but the reality is a little more mundane. Planetary protection is focused on limiting biological contamination of other worlds with terrestrial organisms. That's organisms from Earth, and preventing the return of harmful potential extraterrestrial organisms or just organic materials when samples are returned to Earth during robotic sample return, or in the future, when astronauts come back to Earth from exploration missions to other worlds.
We send things all over the place, and the next big mission is, of course, Perseverance, and it's going to Mars. And so when NASA wants to send a new rover to Mars, what do you do?
Well, Jim, right from the very earliest phase of mission design, when that light bulb first comes on with an idea for a new mission, the Office of Planetary Protection provides guidance to the engineering team on heat sterilization or alternative chemical cleaning methods such as vapor hydrogen peroxide, because some spacecraft materials can be cleaned and others cannot. And we want to be sure that we're designing a spacecraft that'll tolerate the cleaning procedures necessary to go to the three places we care about right now most deeply in terms of contamination, and that's Mars, Enceladus, and Europa. And when we have a mission that's being assembled for one of those locations, then there's actually an independent auditor from our office that travels to all the facilities where parts like solar panels or parachutes are being manufactured, and we take samples to determine the level of biological cleanliness. And every day I actually review data on the number of spores being sampled and detected on Perseverance as we get ready for launch. And we use that to tell us if we need to do additional cleaning, or what we call bioburden reduction, to get ready for launch.
So Lisa, what is a spore exactly? Is it biologically made up of many different things?
A spore is a tiny microscopic resting cell that only certain types of bacteria can make. And they make spores, a process called sporulation, when the environmental conditions get challenging and it looks like they're going to have to shut down. They're not going to continue to be active. But in the process of making that spore, that single cell entity, they wrap it in layers of highly resistant biopolymers. They seal it off, and thereby they create the possibility of that spore later breaking open and turning back into a viable organism that can replicate and grow. So the reason and this goes back to Viking, it's really the Viking planetary protection biologists that thought this through and said, of all of the entities known on Earth that are biological, the only thing we think that could get on a spacecraft, not be seen in an inspection, and stay viable would be a hardy spore. So we don't even monitor all of the spores, which you would be monitoring if you were making medical devices, like implants and things like that. For us, we actually we take a wipe of a spacecraft surface, or we take a tiny little swab that looks like a slightly large Q-tip, and then we heat shock that sample to kill the wimpy organisms, because we only want to know how much contamination is there that could survive the journey, launch, travel, cruise stage, and the landing and the exposure to another planet. Those are the NASA standard assay, the NSA spores. There are international guidelines for spore cleanliness, and the total mission requirement for all spacecraft elements impacting Mars is 500,000 spores, including the rover, aeroshell, descent stage, and parachute. That sounds like a lot, but the requirement is less than 300 spores per square meter of exposed rover surface. Spores are tiny, barely visible with a light microscope. So 300 spores per square meter can be scaled up and visualized as just 28 tennis balls on an entire football field. That's thousands of times less than what our spacecraft would carry if we didn't build them in a clean room facility, if we didn't constantly wipe them with cleaning fluids specific to biological cleanliness, like 70% isopropyl alcohol, which is what we all now read the labels on our hand sanitizer under the current pandemic to make sure that we're using at least 70%. It's just what we use on spacecraft.
Well, what's riding with Percy, and I like that nickname, Percy.
I do too.
But what's riding with Percy is the Ingenuity helicopter. This is really a fabulous idea. It's what we call a technology demonstration, and we hope it works. But does that also have some sort of planetary protection requirements on it?
Yes, it does. It's been held to about the same standards as that upper deck of the rover, but not nearly as rigorous as the sterilization for the sample tubes and drill or the wheels. And that's because it's a very different kind of activity. It will not in any way be associated with the return of samples to Earth. So part of what we're doing with the tubes and the drill is we're not just worrying about what we take to Mars, that's forward contamination. We're very concerned about what might come back in those samples. That's backward planetary protection. And backward planetary protection ensures that we do not bring something harmful and release it into the terrestrial environment.
Well, I think I have one of these samples and a sample tube right here with me. So when I was out at JPL not too long ago and I went into the lab where they were testing the core, I was able to walk out with one of the cores. So they had just, took this, they just took this circular tube that has a cutting mechanism that cuts into the rock and then creates this core. Then they break it off, and then that is put into a sample tube. And that's what these the sample tube looks like. And as you say, these have to be cleaned really well. There are places on Mars I would dearly love to be able to really interrogate. And one of those places is what we believe, we call them reoccurring slope lineae. This is these long lines of dark material that appear every summer. We now know that many of them, maybe not all of them, but many of them actually could be briny water. What would it take for a rover in planetary protection example to be able to go over and look at that a potential water streak coming out of a crater?
Jim, that's a really good question, and one that I think the Perseverance Rover drilling, caching, assembly prepares us to do, because we have been successful in sterilizing at a high temperature for many, many hours in a way that would meet the requirement for going into a place where we might encounter a liquid water environment. So I actually think that what we're learning from this mission to prepare for sample return is going to put us in a good place to actually design a mission where we're gonna reach towards and in some way sample one of these recurring slope lineae, which I usually just call RSLs, because if I don't, it's a tongue twister. And I also think that what we're learning with the rock drilling system on Perseverance is how we might clean a drilling system that would melt drill into ground ice, or rotary drill into an ice cap.
So Curiosity landed in August of 2012, and so it's been there many years in that environment. Do we expect many spores to have survived on its surfaces?
Jim, even if the physical entity is there, because again, it's made out of very resilient biopolymers, it's extremely unlikely that spore is viable. And that's what matters here. What matters is that an organism can come back to life, grow and replicate and spread. And my feeling is, and I'd love it if we had the opportunity to think this through. My guess is that the Curiosity rover is now clean enough that if it were to encounter an RSL or something interesting to explore, that it would be clean enough that we as an international community, because we would probably discuss this through COSPAR, the Committee on Space Exploration, for which you are NASA's representative to the Planetary Protection Panel.
Sure.
I think we would conclude that spacecraft is now as clean or even cleaner than what we could ever accomplish on Earth, and get it to the launch pad and get it on its way.
Yeah, for all the research that we have done, that really makes sense to me too. Well, big discussions are going on at NASA on how we're going to send humans to Mars. What do we have to do to protect Mars and protect the humans that are there?
We need to get a lot smarter than we are right now, and that's what we're going to do at the moon. The Artemis campaign, the Gateway orbiting facility, and extended missions down to the surface of the moon, that's the proving ground for Mars, Jim. If we can study how the microbes from humans leak out of the cuffs of our spacesuit, or get out of the air handling systems in our habitats, or trail along behind us on the wheels of our vehicles, then we'll learn how to prevent that, or we'll develop technologies for sterilization of material when we're at Mars, and then we'll be able to do that exploration without causing harmful contamination of Mars. And I say that because we don't know right now. We don't have the data we need to understand whether or not there's indigenous Martian life. We're pretty sure there's nothing at the surface, because we've been looking from orbit, we've been looking from rovers, we've been looking from platforms. We don't see anything with the characteristics of life as we know it on Earth. But subsurface, if it was ever there and it evolved and adapted, then I think it's quite possible it retreated into the subsurface, where we believe there is, to the present day, liquid water below the ice table. And we certainly do not want to do something that would contaminate or compete with a potential Martian life form before we've had a chance to study it and understand it. It would be our first, our first contact. And that's a,
Yeah, right.
that's a one time only, don't mess it up kind of, kind of event in exploration.
It would be. It would be. Well, I'm gonna I'm not gonna speculate, but I'm gonna think about a potential future, and that is, let's say we find life on Mars. Is it possible that we could, and it's below the surface, it's subsurface, maybe living in the aquifers where there's water, and there's a lot of possibilities for that because we have an enormous amount of life below our feet too, on this planet. Do you think we could get to the point where humans and these Martians could coexist, and what would that look like?
Well, Jim, like you, I'm sort of a hopeless optimist about what scientists and engineers are capable of doing, and I think it is possible. But I think we need to understand it, and be aware of how we would biobarrier, or very carefully control our waste, and our agriculture. Because if we're gonna be up there for extended periods of time, we need to be able to grow our own food, and that's a very different microbiome from just the human body, which we know has a signature. But when we start growing food, now we've got individual organisms that live on and on the roots of plants, mycorrhizal fungi that have a distinct characteristic, and bacteria as well. So we need to be very, very careful initially so we don't do something inadvertent and irreversible. And then I think there is a possibility in the future that we can be there and we can study. Frankly, we're going to have to learn, if there is something in the subsurface, how to not have it get inside our habitats, and in some way present harmful contamination to us. It's a very complicated, very complicated relationship we'll have to develop. But again, in the same way that the moon is the proving ground for Mars, I think Mars is the proving ground for the extraordinary icy worlds that are out there, around Saturn and Jupiter. Let's make sure we know what we're doing in a very dry, hostile, cold terrestrial planet before we go to an icy moon.
I'm going to guess that you believe there's life beyond Earth.
Jim, I would be absolutely flabbergasted if there was not life elsewhere in our solar system, because I think evolutionary biology has really changed over just the past 2 decades. And once we began to realize that there is essentially no place on Earth that doesn't have living organisms, it makes it very hard for me to think that life only got started here. The very fact that we don't know what the origin of life is on Earth, we don't have a geologic record that gets us back in time far enough with unaltered materials to know what the origin looked like on Earth, also makes me wonder if the origin was someplace else and something arrived on Earth ready to go, or partially formed, or and any of those ideas makes me keep my mind open about life elsewhere in our solar system. If it's there any place else in our solar system, then I think we will have to conclude that on the spectrum from rare to common, that it's going to be common. If we don't find any vestige of a life form anyplace else in our solar system, that's gonna push us towards rare.
Well, when you look out into the solar system, where do you think we will find it first?
I'm still cautiously optimistic about Mars because of the methane mystery. We see these pulses of elevated methane in the atmosphere. And not only do we have no explanation for where that methane comes from, we don't have an explanation for how that methane is removed from the atmosphere. We have a great mystery on Mars right now. And that's why, as the Planetary Protection Officer, I want to see us continue to explore with a very, very careful eye on forward contamination. that gets back to your question about can we go there and sustain ourselves without harming Mars if there's something on Mars that could be harmed. Ultimately, I think it's a better bet to look in the oceans beneath the ice covers in places like Europa and Enceladus.
So let's say we brought the samples back from Percy, and now we've started to interrogate them. Do you think we know enough to be able to say these samples, we can delineate things that we brought that actually have come back from those things that are indigenous to Mars?
Jim, that would be a false positive. It would mean could we or do we need to worry about being confused and misidentifying something that made a round trip with something that came from Mars itself? I frankly, and we've spent a lot of time discussing this with outside experts, I have very little worry about a false positive. And the reason for that is that we are archiving samples from the spacecraft, from the facility, from the launch pad, and we are storing and saving those samples for future study so that we know a great deal about everything that could have potentially gotten on that spacecraft and flown with us.
Wow, that sounds great. Well, Lisa, I always like to ask my guests to tell me what was that event or person, place, or thing that happened to them that got them so excited about being the scientists they are today. And I call that a gravity assist. So, Lisa, what was your gravity assist?
Jim, it's hard for me to point to a single event because I think you're aware that I had quite a number of not false starts, but moved down one path with my education and then said, this really doesn't interest me that much. I went off to college as a Spanish major. Wow. Even though I had taken a lot of math and science in high school and knew that was something I was good at, I didn't see any role models. I didn't see any way that was going to work out. And then I realized that I really still fundamentally loved biology in particular. So I started taking biology classes, and then I decided I didn't want to be killing frogs in biology labs. This was at a time when we were still working with live animals in undergraduate labs, right. And had an inspirational moment when I decided I'm a botanist. Plants don't bleed. So I actually transferred to the University of North Carolina as a botany major. And then if there was a sort of pivotal gravity assist for me, it was in my senior year when I took my first geology course. And the instructor, John Dennison at Chapel Hill, had a way of talking about time travel through study of the geologic record, through stratigraphy, that was so awe-inspiring that I knew that I was even more passionate and more interested in the history of life on Earth and the evolution of life on Earth through the study of the ancient record. I was more interested in that than living plants, and so that's my. I guess that's my gravity assist, and it's what serendipitously gave me a dual degrees in life sciences and earth sciences that actually positioned me ultimately to be competitive for the Planetary Protection Officer position when it was advertised and opened 3 years ago.
I was just so delighted that you applied. What made you decide to do that?
This is kind of a strange and wonderful story about role reversal. So a number of people, both inside and outside NASA, had let me know that the position was open, and I kept saying, no, maybe 10 years ago. It's too late in my career. And I made the mistake, well, maybe it was a mistake, maybe it's the best thing that could have happened. I was talking to my daughter about it. She's an engineering graduate student at Stanford. And I said, this position is open. And that began weeks of relentless work on her part to talk me into applying. And I kept saying, no, it's just too late. And then finally, one time on a phone call, and this was 3 days before the position was going to close for applications, she said to me, so, Mom, following your passion and reaching for your dream job is advice you can dish out, but you can't take it yourself. And I was so shocked that this 25-year-old threw back at me what I throw at her, that I actually said, you know what? I'm going to apply. I'll never be selected, but I'm going to apply. And for the rest of your life, you're going to say to me, I'm so proud of you for applying. And then, the unexpected happened. And I have had the most wonderful 2.5 years to date of being the Planetary Protection Officer and helping NASA find ways to not contaminate forward or backward. It's a gift that Isabel gave me.
Well, I got to tell you, I'm so proud of you for applying, because I have enjoyed working with you over the last several years. It's just been a wonderful experience for me, too. Well, thanks so much for tagging up with me today to discuss what a Planetary Protection Officer does and how they do it. I've really enjoyed our discussion today.
Hey, Jim, I'm just delighted that you asked and we had a chance. You caught me off guard with a couple of these questions, but the speculation was lots of fun, and go Perseverance.
Go Perseverance. Join me next time as we continue our journey to look for life beyond Earth. I'm Jim Green, and this is your Gravity Assist.